Okay, so good morning once again, my wonderful and amazing students. I'm sure we had a wonderful night. So we continue in our study on equilibria in solution. We have made progress. We have been able to see the importance of equilibria in solution, how it affects our daily lives. We've seen the importance of the measurement of pH and, of course, pOH of any aqueous system. And, of course, we've also seen that solutions or dissolved substances can be classified as strong or weak electrolytes. And, of course, for strong electrolytes, we actually have no problem. Whatever ions are formed in solution will be dependent on the amount of the salt or the amount of the substance that's dissolved, since the electrolytes will undergo complete ionization as but however, for weak electrolytes, we know that even though the electrolyte will ionize to give some ions in solution, some of the electrolyte will still remain as undissolved in solution, such that an equilibrium is established between the undissolved substance and the ions formed from it, which are usually very small anyway. And of course, we can take advantage of that to determine the equilibrium constant. If it's an acid, we call that the acid dissociation constant. If it's a base, we call that a base dissociation constant. In our last lecture, we looked at HPAC and HPR. So today, we'll be looking at base dissociation constant. Base dissociation constant. All right. So we're about to answer this problem when we run out of time yesterday. All right. Let's have a look at that. Okay. So the question here says dimethylamine, a key intermediate in detergent manufacture, has a base dissociation constant of 5.9 to the power of -4. What is the pH of a 1.5 molar solution of dimethylamine? Okay, the solutions are provided here, but like like I did mention in our last lecture, that the bluntest pen is sharper than the sharpest brain. Maybe we should work it together so that you can appreciate what is being displayed here. All right, let's have a look at it together. So we have dimethylamine, CH3, 2 NH, dissolving in water to give us now dimethylamine is a proton acceptor. So if you take proton from water and gives us this dimethyl ammonium ion, CH3 2 NH2 plus OH minus. All right, so that is the expression for the equilibrium. Now let's set up our ICE table as we used to do. So we have I, C, and of course E. All right, we are told that we have 1.5 molar of this dimethylamine. Initially, of course, none of this will have been present. Of course, none of this will be present. Now, what changes will have occurred at equilibrium? Now, that takes us back again to stoichiometry. See, I keep mentioning stoichiometry, just to illustrate the importance of stoichiometry in chemical calculations. That's why I want to advise you, my students, please try to understand your stoichiometry very well. All right, having said that, a careful look at this expression will show that when 1 molar of dimethylamine is consumed, 1 molar of dimethyl ammonium ion will be formed, and 1 molar of hydroxide ion will be formed. In one word, by the time X mole of dimethylamine is consumed, then of course X moles of dimethyl ammonium ion will have been formed, and X moles of OH minus also will have been formed. So the change that will occur here is, since it's 1 ratio 1 to 1 to 1. All right, since we have ratio 1 to 1 to 1, then if X of this is consumed, then of course X of this will have been formed, and of course X of this also will have been formed, such that what is the concentration at equilibrium now become, for this is 1.5 minus X molar, and of course this will be 0 plus X, which is X molar, and of course this also is X molar. All right, so this now, we can now use this to say, okay, the expression for the equilibrium constant, now this is a base that dissociates, we call it base dissociation constant. Base dissociation constant. All right, and that becomes CH3 to NH2 plus, then OH minus over the undissociated base CH3 to NH. All right. Now, if we substitute for these terms, then we're going to have this to be equals to X over 1.5 minus X. Now we are told, let's quickly check. All right, we are told that the KB of this base is 5.9 to the power of minus 4. All right, let's do that. 5 to the power of minus 4, 5.9 to the power of minus 4. All right, so this become, that is 5.9 to the power of minus 4 will be equals to X squared over 1.5 minus X. All right, in this case now, we have to solve quadratically. But like I said in our last lecture, a simplified approach is to assume, because of course the value is very small, the value of the KB is very small, is to assume that X is very, very small compared to 1.5. Somebody who has 1.5 million naira and is spending spending 50,000 naira for 1.5 million. By the time you have spent 50,000, you'll be left with 1,450,000, which is like you have not spent anything. All right, so I'm sure you like money. That's why I'm using money to illustrate this. All right, so we can then say, assume X is far, far less than 1.5, such that we can say that 1.5 minus X is approximately equal to 1.5. All right, so this implies therefore that 5.9 to the power of minus 4 will be equals to X squared over 1.5, such that X squared now sorry, let me, don't worry, maybe I could turn it. Oops, I can't turn it. Okay. Okay, my tab is not allowing me to write very well, so let me write it here. Sorry. Permit me to write it as to make life easy so we can manage this space here. All right, this is it. This is very easy for me now. All right, so we can say this is 5.9 times 10 raised to the power minus 4 times 1.5 is equals to x squared. That is, now let's see what value that's going to give us. So I'm with my calculator, and I want you also to join me as we solve it together. Please bring out your calculator. All right, so we have, so we can just find what x is. So x will be equal to square root of 1.5 times 5.9 exponential minus 4, and that will be equals to 0.0297. Okay, so x is simply equals to 0.0297 molar. Now, before we continue, we want to first justify that our assumption is correct. We want to establish that the assumption is correct. Otherwise, we have to solve quadratically. And how to do that is to find out what the percentage dissociation. All right, so that's the next thing we're going to do now. Okay, so let's see what the percent dissociation is. So we can write percent dissociation will be equals to the amount that I've dissociated, which we find out to be equals to 0.0297 over the initial amount 1.5 times 100%. And in that wise, our value is about 2%. Let's get the exact value so we don't just follow what's on the screen. That's 1.98. So this 1.98%, which of course is far, far less than 5. And so that assumption is reasonable. So now that we have justified that justified our assumption, that's a reasonable assumption. The next thing to do is to calculate the pH as we are asked to determine. Now, what we have been able to do here, if you go back to flip back to the previous slide here, is that OH is equal to X molar. Okay, and X is equal to 0.0297 molar. So OH is equal to 0.0297. Don't forget what we're asked to determine is pH. Now, to do that, you see that you calculate pOH or you calculate hydrogen ion concentration. Either way you go, you're going to get the same answer. Either way you go. You might want to first determine what pOH is, and also we can say pOH is equals to minus log to base 10 of OH concentration, which is equals to minus log to base 10 of 0.0297. And let's see what that's going to give us. And that'll give us 1.53. All right. Okay, so this is equals to 1.53. Now that we know pOH because of 1.53, remember that pH plus pOH is equals to 14. And so therefore pH will be equals to 14 minus 1.53, which of course will be equals to 12.47. All right, that's one way to go about it, and you calculate the pH to be 12.47. Alternatively, you may want to determine, you may want to go through this route that says for any aqueous solution, AHOH minus is equals to 1 to the power minus 14. and such that you can know what H plus is, will be equals to 1 to the power of minus 14 over 0.0297. All right. So once you know that, you can now use that to calculate the pH. I think at that junction, I could allow you to finish that on your own. I mean, all you need to do is get the hydrogen atom concentration and then get the minus log of the hydrogen atom concentration, and you get the same answer as I've obtained previously. Now, why the little difference between the answer at 12.47 and 12.48, of course, we can know is because of the approximations involved. Okay, but then it is very negligibly small. Okay, so that is that about the KB, and I'm sure with this, there is no question. I want to believe there shouldn't be any question given you on acid dissociation, base dissociation that you cannot answer. Just first make the assumption the amount dissociated is negligibly small compared to the initial amount of the base or the acid. Okay, so from there you can calculate your parameters, justify the assumption. Once the percent dissociation is less than 5, then less than or equals to 5, then you are good to go with your assumption. Then you can calculate whatever it is you are asked to calculate. Otherwise, if the percent dissociation is greater than 5, you might have to solve quadratic expression. I'm sure there is nobody here who will not be able to solve a quadratic expression. I hope we are all clear with that. All right. Now, having concluded this, before we start the next class, I think it's better for us to take our first code for the attendance this morning. So let's take the code. I'm coming. I want to write it for you now. Okay, while waiting for the code, let me see what's your view about the class. I know you like money. Yes, somebody said that. Tobi Akiyemi, I know you like money. Well done. Well done. I also like money too. That's why my name is Owoyomi. You know, and my name is biblical. Money answered all. Money delivers. Okay. Yes. All right, so while waiting for the code, we are not going to waste time. We'll continue with the class while I await the code from the source. All right, so with this now, we have concluded on the acid-base equilibrium. Now, there's a question. You know, usually when we're in secondary school, we're taught acid-base reaction, and we call it neutralization. Okay, the reaction between an acid and a base was generally then, and erroneously so, called neutralization. Well, it is not every acid-based reaction that is neutralization. Neutralization is exclusively the reaction between a strong acid and a strong base. Between a strong acid and a strong base, resulting in the formation of a neutral salt. Resulting in the formation of a neutral salt. When we say neutral salt, a salt that is neither acidic nor basic, such that at the end of the reaction, the pH of the solution will be 7. That is what we call neutralization reaction. However, for any acid-base combination, after the completion of the reaction, if the pH is either greater than 7 or less than 7, then the reaction is no longer neutralization. And what could cause the pH to be greater than 7 or less than 7 is exactly what we're about to consider. For example, consider the reaction between a weak acid and a strong base. Weak acid, strong base. A weak acid like acetic acid or ethanoic acid reacting with a strong base like sodium hydroxide. All right. What will happen in such a reaction is what we are trying to look at in this class. And of course, similarly, if you look at the reaction between a strong acid and a weak base, for example, the reaction between hydrochloric acid and ammonia, to give ammonium chloride. Now, hydrochloric acid is strong acid. Ammonia is a weak base. The solution of ammonium chloride will not give a solution that has a pH of 7. The pH automatically will be less than 7 because the salt is formed from the combination of a strong acid and a weak base. Okay, similarly, like the previous example I gave, between ethanoic acid and sodium hydroxide, a weak acid on one hand, a strong base on the other hand, to give us sodium ethanoate. That's the salt form. The solution of sodium ethanoate will have a pH that is greater than 7 because it is formed from a strong base and a weak acid. How can we account for these pH differences? That's what we are considering in this set of lectures. All right, I've explained all that. All we have on this slide now is what I've explained. As a for ion in solution, hydrolysis is the reaction of the ion with water, in which proton transfer occurs. So when an ion reacts with water, a proton transfer reaction will occur. Okay, like you have here, most ionic salt will dissolve in water to form oppositely charged ions, which are hydrated. Okay, most ionic salt will dissolve in water to form oppositely charged ions, which are hydrated. The subsequent reaction of these ions with water is what we call hydrolysis. So the reaction of ions with water is, in this case, referred to as hydrolysis. All right, like I said, it's not every ion that undergo hydrolysis. There are only 2 types of ion to be considered here. An anion, that's a conjugate base of a weak acid. Now, don't get. I'm going to explain all this. I want to please just give me your attention. So when we have a weak acid, like for example, we have ethanoic acid, like I said, CH3. COOH, aqueous. We know that when this dissolves in solution, it gives acetate ion, otherwise known as ethanoic ion, plus hydrogen ion. Now, this acetate ion now will then react with water. Of course, when hydrogen ion reacts with water, it's going to form hydrozonium ion. Okay, so if hydrogen should react with water, it's going to give you H3O plus, which is more or less hydrated hydrogen ion. However, when this anion from this acid now that let's explain it. This is the acid, and this is the conjugate base of the acid. Why is it a conjugate base? Let's explain that. Let's come here and write it in full. What really happened in solution is actually this reacting with water. Okay. This is a reaction with water, and of course, that's why we call it aqueous, and it gives acetate ion plus H hydrated hydrogen ion. All right. Now, here in this reaction, this is the acid. It's a proton donor. It's donating proton to water. So this is acid. What is formed when this proton have been removed is the conjugate base of this acid. So this is the conjugate base. Okay, that's what I'm trying to explain here. Now, in this reaction now, water is acting as a base because it's the proton acceptor. It's accepting proton. And so this is the base. And because it had accepted proton, it's formed this is the conjugate acid. Okay, so that's what all this that I have here is trying to explain. Okay, that an anion that's a conjugate base of a weak acid, like the acetate ion. A cation that's a conjugate acid of a weak base. For example, let's illustrate that also, so that we can understand. Okay, let's look at ammonia now. Now, ammonia reacting with water. Ammonia dissolved in water to give us ammonium ion plus OH minus plus OH minus. So you can see in this reaction, ammonia is a proton acceptor, so it's a base. And because it has accepted proton, it formed ammonium ion. So the ammonium ion form is the conjugate acid of ammonia. Now, ammonia is a weak base, and so the conjugate acid of a weak base. So in any solution where you have ammonium ion and you have acetate ion with water, that's hydrolysis. Ammonium ion also react with water, that's hydrolysis. That's what we mean by hydrolysis. I hope that is clear enough. Now, before we continue, please let's take our attendance. Please let's take our attendance. The first code for today is 22 XAW. XAW in capital. 22 XAW. So let's take that now as our attendance. All right. Hope you're all there. Please log into the attendance page now and do the needful. All right, so like I just illustrated in our previous example with acetate ion being the conjugate base of acetic acid. Now, because acetic acid is a weak acid, the ion formed from this weak acid will now react with water to form acetic acid plus OH. And so this reaction here is what we call hydrolysis. Sorry, what we have here is equilibrium sign. It's only that the machine I'm using here cannot see the software. I use math math type to type this something. That's why I couldn't see it. So you have the on top of it KH. All right. So this is hydrolysis. This acetate ion, the conjugate base of a weak acid, reacting with water to form acetic acid and OH. So the equilibrium constant for this reaction is called hydrolysis constant. It's called hydrolysis. In this case, is acid hydrolysis constant. And of course, like you're familiar, this will be equal to the KH will be equal to concentration of acetic acid plus OH minus over the acetate ion. Okay. Now, something is emerging from here now. Something interesting is emerging from this concept. Now let's look, because this acetate ion is actually from acetic acid. Let's look at acetic acid itself. In water, it gives acetate ion plus hydroxonium ion. All right. Now, this, of course, is association, and that will be equals to CH3 COO minus H plus over acetic acid undissociated. All right, that's what Ka. Can we establish a relationship between this KH and Ka? I want us to look at it carefully. I want you to look at it carefully with me. Can we possibly establish a relationship? You can use either KH or Ka. Now, let me use KH. Let somebody else use Ka. I'm going to use KH here, and I want somebody else to please help me use Ka. And just see what I want to do now. From the KH, if I multiply this by hydrogen ion, I'll multiply this also by hydrogen ion. Does it make sense to you? I've just multiplied them by a constant. All right. If I look at that carefully, then I'm going to have here, where do I write? Okay, I'm going to write it here. So I'm going to have CH. Sorry, please. Sorry for that short break in transmission. All right, so let's come back here. So I'm going to write this as CH3 COOH. Now, OH plus HKW, I'm sure you remember that, is KW over CH3 COO minus H plus. Okay, what I've done here is this and this is what we've combined to give us KW. All right, so I have this. Now, if you look at what is left and compare with this, you will notice, if you can notice that carefully, you will see here that what I have here, CH3COH, is the inverse of what I have here. What I have here is not the inverse of this. So that means, therefore, this will be equals to KW over KA. That is, KH is equals to KW over KH. That is KH. All right. So you can see the relationship now. If I know KH, if I know KH, I can know KA because KW is a constant. If I know KA, I can know KH because KW is a constant. I'm sure this is clear. Of course, we're going to see it in the next slide. I'm just trying to join you to understand the concept. Like I said, somebody should help me to do the same here. What you need to do here is just multiply this by OH, multiply this by OH, and see what you're going to get. To also get what we have here. It's very interesting. I'm sure we are getting it. Okay. Oh, sorry. I even have a space. I didn't even have a space here. All right. That makes it easy. Of course, I've written what I meant to write here. So what we have there simply is that the KH we have obtained is simply equals to KW over KA. All right. That's what I've just derived in the previous slide. Okay. Let's see what happened to the next. All right, what you have there is just what I've just explained now. All right, so the extent to which hydrolysis of the acetyl occurs is then inversely proportional to the strength of its conjugate acid, because the extent of hydrolysis is measured by the KH. Okay, maybe I'm too fast. Let's go back to the previous slide. Okay, this is what we are saying here. This is a measure of the extent, okay, of the strength of the ion, hydrolysis of the ion. And of course, this is a measure of the extent of dissociation of the acid. So what I've just said here is that at the extent to which the ion, the hydrolysis of the ion occur is inversely proportional to the strength of its conjugate acid. Let's go back again to it. That's what we're saying here. Okay, the hydrolysis is inversely proportional to Ka. I hope that is clear for everybody to understand. All right, let's make progress. Okay, so generally, the extent of hydrolysis of the conjugate base 2 of an acid, the extent of hydrolysis of the conjugate base of an acid is inversely proportional to the strength of the acid. I'm just repeating myself, saying the same thing all over and all over again. Now let's look at the hydrolysis of a positively charged metal ions from sparingly soluble salt, usually formed from the reaction of a strong acid and a weak base, such, for example, as ammonium ion. Okay, ammonium chloride. Now let's see that. Okay, so this is ammonium ion from ammonia. That's the conjugate acid of a weak base. It will also react with water to form a place. Like I said, let me correct this here because the system here could not see the software I use. That's why it's an equilibrium process, please. Okay. So what we have there is what I'm writing here, NH4 plus reacting with water to give us an equilibrium sign. And I write, okay, equilibrium sign to give us ammonia and H3O plus. On top of this, I have KH. Okay, so that's what we have here, please. All right. Now, this KH, of course, will be equal to the concentration of ammonia multiplied by concentration of hydrozonium ion multiplied by the concentration of the ion, the cation, which is the conjugate acid of the weak base. Now, if we consider, just as we did for acetic acid, so here, if we consider the dissociation of ammonia, please again, don't forget the sign here. Maybe, I don't know, let me just circle it. What I've circled is this is an equilibrium sign, and of course I have Kb on top of it. That's what I've circled. Okay, all right. So the base dissociation constant, of course, will be equal to ammonium ion multiplied by ion concentration divided by ammonia concentration. Now, just as I did in the previous one, I could use this or this. This time around now, let me use this now. I've used KH in the other one. Let me use KB here now. Now, what I will do is just here, multiply this by hydrogen ion. And if you do that, you multiply this also by hydrogen ion. or hydrozonium ion. Now, what you have here, the product here is simply Kw. It's simply Kw. So this becomes what you have here becomes Kw multiplied by ammonium ion concentration all divided by ammonia multiplied by hydrogen or hydroxonium ion. Okay, that's what you have here. Now, take a look at this. What we have here is just the inverse of what we have here. And so that means that, therefore, the Kb will simply be equals to Kw over Kh. Or you can write also as Kh is equals to Kw over Kb. Because if you have done what I've done here, if you have done similar thing to this place, instead of H, now you multiply it by OH. And if you multiply it by OH, you multiply it also by OH. And here will be Kw. And what is left is NH3 over NH4OH, which is the inverse of this. Okay? So either way you go, you're going to get the same thing. I'm sure, I hope it's clear to a number of us. Let me hear what your comment is. While I'm looking at your comment, let's take the second code. The second code for today's class is DAA9F. 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 Please log in for the attendance, please. DAA9F. Dayo Akintunde Akinfenwa 9 Folorunsho. Dayo Akintunde Akinfenwa 9 Folorunsho. That is the second code. Okay? I just want to hear what's your comment. Okay, Tayo Edo, you may have to relocate to where you can hear because others are hearing me loud and clear from their comments. All right, others are hearing me. Thank you. So you can hear clearly now. Oguta or Jeshu Tofumi, what is that you cannot understand? Please let me know in the comments. You can write what you don't understand. Maybe I can find time to explain before we run out of time. The attendance page is not responding. All right. We will look at that. The attendance page not responding. It's okay. We will see what we can do, but just keep checking. It will. A number of students are saying they do not understand. All right. I would like to know. Adewale Timileyin, you don't understand too. Okay, that's all right. But I want you to be calm. You see, you want to understand this concept. You need to be calm and concentrate your mind to what I'm teaching. I will explain it again. Don't worry. All right, don't worry. I will explain it again. Just calm down. Let's go back to it. I will rush through because of time constraints. But then, please, I want to give me your attention so they can understand the concept very well. It's important that you get it right. Let's go back to class. All right. Okay, I'm going to explain myself now. All right, so we have ammonium ion. Undergoing hydrolysis to give us ammonia plus hydroxonium ion. All right, because this is a proton donor. NH4 is a proton donor donating protons to H2O. And when it donates proton, it forms NH3. And when this accepted proton, it becomes H3O plus. This process is called hydrolysis. So let's call it KH. The hydrolysis constant here, KH, will be equals to NH3 concentration, H3O plus over NH3. Let's keep that in abeyance for now. We have said that this ammonium ion is actually formed from a weak base ammonia. Okay, so let's look at the reaction of ammonia also with water. In this case, it's not hydrolysis really, it's dissociation of ammonia, a weak base, now plus water. So we call this Kb because it's a base and it gives NH4 plus OH minus. In this case, ammonia is a base, a proton acceptor taking proton from water. So you can see in these two reactions now, water here is a base, water here is an acid. That's explaining the fact that water is amphoteric. I hope you are following that. All right. Okay, so if that is true, of course it is, we can write that Kb is equals to ammonium ion OH minus over ammonia. Now, I hope this is clear now for those who said they couldn't get it. Now, what we are trying to do, don't be agitated. Look at either of them. You can work with either of them. I may decide to work with Kb. Here, let me rewrite Kb. I want to see, can I establish a relationship between Kb and Kh? That's the objective. The objective is, I want to see, can we establish a relationship between the two of them? We can. And I want us to become, you can use this, and I will appreciate those that do not understand. As I'm working with Kb, you also think of what you can do with Kh to get Kb. Now, Kb is equals to ammonium ion OH minus over NH3. I say multiply this numerator by H3O plus. If you do that, you have to multiply the denominator also by H3O plus. And if you do that, you wouldn't have committed any crime because H3O plus will naturally cancel H3O plus. Okay? And you'll still be left with your Kb. Now, this, of course, becomes NH4 plus. Now, the product of OH and H3O is what we call Kw, auto-ionization constant of water, that we call Kw 1 times 10 to the power minus 14. We've been doing this in our previous class. Now, divide this by NH3, H3O plus. Now, if you look at this, and you look at this, no, sorry, please, this should be NH4. I'm sorry, that should be NH4 plus, because that's the reactant NH4. Okay, so if you look at this very carefully, and look at this, you can see here NH3, H3O, H3O are the denominator. Now they have become numerator A. NH4 is the denominator A. It has become the numerator A. So this is, I can write this as U KW times NH4 plus over NH3 H3O plus. Okay, everything here is the reverse of this. Okay, So that means that this is equals to Kw over Kh. So Kb is Kw over Kh, or alternatively, or conversely, Kh will also be equals to Kw over Kb. That's what you will have obtained if you have multiplied this by OH and OH. Okay, this is what you have obtained, which is, so what we are saying is the extent of hydrolysis of the ion is inversely proportional to the strength of the base. The extent of hydrolysis of the conjugate acid is inversely proportional to the strength of the weak base. Okay, I hope that is clear now. Let me hear what your comment is now, if you now understand what I've done. All right, I've just explained now Taufiko. All right, Adura Leri, okay. I've just explained now. I've just explained. I hope. Yes, water is not. Yes, water is liquid. So for solid and liquid, the concentration does not change at all reasonably during either dissociation or hydrolysis. So it remain fairly constant. So we don't reckon with the concentration of water. Okay, we don't reckon with the concentration of water when you're writing equilibrium constant. Same thing go for. Don't worry, when we look at types of equilibrium, which often have taught, but there was a mix of, that's why, but I'm still going to explain that before we conclude the class. All right. Are we to apply with only hydrozonium ion? Of course not. What happened? Okay, live streaming. Okay. Okay, I hope you're now getting it now. Thank you very much. Can you multiply with OH? You can multiply with OH if you have identity FC bar. You're asking if you can multiply with OH. Yes, you can. But that means that you will have H3O plus or hydrogen ion as one of the components of the numerator. So that if you multiply by OH, the product of the two will give you KW. All right. I hope that is clear. All right. Well, we may not be able to go beyond this today in today's class because of these questions, but it's okay. It's worth it. Hopefully, when next we meet, that'll be tomorrow is Wednesday. Yes, when next we meet, we will look at examples of that. Before we go, let's quickly take the last code. All right, the last code for today's class is 8GE27. 8 Godwin Emmanuel 27. 8 Godwin Emmanuel 27. 8GE27. All right, I hope to see you again tomorrow by the grace of the Almighty. Please, before coming for class tomorrow, it's like a number of you have challenges understanding the concept taught today. And so that should be a challenge for you to go through it again and again before you come for lecture. So that by the time we'll be solving problems, related problems now, it should, because this is an important topic, okay? And by the time we begin to solve related problems, it won't be difficult for you to understand. So please take your time to go through this lecture. And I've been informed that this lecture is YouTube. So for those of you who are asking for slide, I want you to please take your time, look for it on YouTube and listen to it again and again. All right. So thank you very much. Have a wonderful, wonderful day. Well, I'm still in your class, following what by Damosi Yusuf. Please check the lecture online, please. The attendants keep telling you to reload the page. The attendance is not responding. That cannot be true. Okay, can you draw questions that the percentage of the solution is greater than 5 and leads to quadratic equations? We could do that at the Miriam, but the challenge is time. Now, for us to now be solving, I could drop such question for you to practice, but we're not able to answer such question in class because of time constraints.
The form is going.
The form is going. Ugochukwu Eze, the form is going, please. It's going. It's going. Please check it again. Or maybe you've run out of data. All right. Thank you, American boy. Attendance submitted. Thank you. How can you get the slide to revise? I said the lecture is on YouTube. Is that true, sir? The lecture is on YouTube. I think the attendance can open from Blue. Well, sorry about that. Maybe you use MTN or use whatever means. Just submit your attendance. Okay? Or let me see who's saying that. Emmanuel. Okay, Emmanuel, maybe I should buy you MTN line from my meager salary. The attendance is going. Anna Faith, that is not true. But so Mohammed Nafi just submitted now. Khalid Adoto Yibo just submitted now. So Anna Faith is not true. That is not going. Please. All right, I'm logging out. Bye-bye. No, no, university, university. What are you? Come on, go, you know.